Are we living in a simulation?
That's a question I think I've been asking since high school when I saw The Matrix.
What is this 3D Gaussian splatting?
3D Gaussian splatting has a marketing problem.
From each and every Gaussian, there will be only one splat, or it will be a multiple?
Gaussians could be shaped like a football. It could be shaped more like a basketball. When we talk about accuracy of 3D Gaussian splatting, it's an apples and oranges. This whole scene is 40 Gaussians that have been basically predicted using Tesla's what's called world model.
Where do you see the main bottleneck right now?
2D is against my religion.
Before we jump into 3D Gaussian splatting and simulations and everything else, I actually have a question regarding the simulation, because just a few days ago, there were like mass flood with the Genie free videos.
Yep.
And it just sparked all over one question for me: are we living in a simulation?
That's a question I think I've been asking since high school when I saw The Matrix.
Yeah. I just had to rewatch it just 2 days ago.
Yeah. Oh boy, that was a fun movie to watch with my son. No, I don't think we're living in a simulation.
You're not in this thought.
It's a fun thought experiment. I always wonder if billionaires just play life like it's a big simulation game.
I must say that I'm the opposite team, because with all of the development and the speed of how everything is changing and developing so fast, I really fall into the group that thinks that we actually might be living not in a base reality.
You know, they got some really good high-end compute somewhere if they were all living in a big simulation. They have cracked the quantum computing.
Why not?
Yeah, no. That was a fun to see Genie 3 come out. I am yet to test it. I don't want to drop $250. I'm not even, is it even live in your country? It's only live in a certain select country.
It's not. I don't think. Is it even live in United States? I think only beta testers are allowed to use it right now, right?
They opened it to anyone who has a Google Ultra account, which is like $250 a month, or even more if you don't.
Is it the highest?
Yeah, they're highest tier. Yeah.
Okay.
I just don't have a use for it right now. It was getting a little tiring on X because it kind of took over my X feed, where I get a good amount of live news, what's happening in the tech world. But a lot of people are saying like, oh, I made, check out this. This is like basically replacing games. But if you watch it, it's just people walking, like they're all just navigational tasks. So everything you watch is like someone surfing, which was kind of cool, or someone walking through a city, and like this is the new GTA 4. Or 6, I mean, but think of all the game developers who are just getting, like thrown to the wolves, saying like, "Oh, your job's gone." But there's so much more involved in an actual experience that people want. To me, this is just kind of like a generative AI slop at the start here, because the novelty is going to wear off fast. It's like, "Oh, cool! I walked through this scene. I now walk through this scene," and then after you do that for like one day, you're going to be like, "I don't see the draw to bring me back to walking through things."
It is interactive from the very beginning, so you can actually move the character or the car or whatever you have there. So,
yeah, you craft a scene and you
really
craft.
Here's deep, right?
Yeah, so it's really impressive what they built. I just we'll get into that technology. I was going to talk about that, but there's some like purpose-built applications people are building using the same core technology that I think is really going to be interesting to watch. And Genie 3 is kind of interesting because you build this model. We'll get into that, but you build this model, and then there's a bunch of different ways you can inference on it. You can basically have it create things for you. And so, being that advanced, there's like probably 10 new products they could create off of that to do purpose things. It's just how you want to tune it.
I totally get your point with like there's much more in gameplay mode and basically whole environment than just navigation. That's totally valid point.
Yeah.
However, it brings me to the beginning of the vibe coding or or just the code generation on ChatGPT, like first weeks or first months, it was the very same discussion, like there's no way this is going to replace coders and programmers, but it is already happening. Okay, like the seniors ones are totally fine so far, but junior positions are just vanishing from every bigger company.
I still argue that, you know, people are saying, oh, do we even need to have people get degrees in programming? Is that degree worthless? I'm not a skilled programmer, but me having enough knowledge in programming, I am better able to steer the vibe coder, right? So I still think, like, even if we're using world models for geospatial tasks and you're in your industry, I think having a geospatial background, you'll better be able to work with these new AI models and get the results you want, or know what is giving you slop faster, some false result.
Definitely incredible times to be alive and to experience.
Yeah.
Perfect. So this whole session, and I mentioned this in a teaser for the webinar, was your message, your DM to me, like saying, I was watching the one with the Michael Glove and I would have many different answers.
Yeah.
So I just said, come and tell them.
Yeah. And I'm not want to ruffle feathers with Michael. We're actually good friends. We talk probably almost every day. Not a lot of his answers weren't wrong, but didn't necessarily either go deep enough or were just kind of like glossed over the technical part. I don't want to be too technical, but it's like, oh, you got like not a complete answer. Which I think some people don't need a complete answer, right? It's like, I don't need to know how an engine works in a car to know how to drive a car. I just need to know that if I push the gas pedal, it'll propel me, hit the stop, the brake, it'll stop me, things like that. But it does, there's, you can having a little bit more understanding of how some of this technology works might help you decide if it's worth your time investing, exploring, or maybe you didn't understand what like triangle splatting really is, and then it might hook you on realizing, oh, I really do need to explore that.
In no way we were trying to like tell something bad about Michael, or that he's not, he does not know what he's talking about or whatever. He's a big professional and he's a great mind and knows a lot about 3D Gaussian splatting. It just came to me as a great idea how to spark the conversation, and then because of course the 3D Gaussian splatting is very complex, and I understand that different professionals might have different opinions. So I'm just glad you are here today. Yep. And we can hear and see some different point of view on the technology and the usage.
Yeah, and I'll probably say something. Someone else will say, "Oh, that was wrong." So yeah,
of course,
you guys can keep me on.
I will invite them to the webinar.
Yeah, that's funny. Yep. So yeah,
perfect. So just for the audience, guys, if you have any question regarding topics that we are discussing right now, please go ahead and just write them in the comments. I'll try to answer or ask Jonathan most of them, and whichever will be interesting, and we'll move our conversation either deeper or further. So let's start with the basic question. In your opinion, what it is 3D Gaussian splatting?
Okay, I made you pitch that to me at the start.
You asked for it.
So one thing that really drives me crazy is there's two concepts here, and they're lumped into one term, which I think has 3D Gaussian splatting has a marketing problem. It's kind of like saying what is laser scanning, and that's an action, versus what is a laser scan, like a point cloud from it. So there's 3D Gaussian splatting, which is to me has always been the action of generating this scene, which is a really cool process. And then there's a 3D Gaussian splats, which is the output of splatting. This is 3D Gaussian splatting. So simple, right? Everyone can understand.
We will stay with this picture for a longer time.
we'll sit with this for a second. So if anyone comes from the world of computer vision or 3D reconstruction from imagery, they will know SFM points. Basically, I go take a bunch of pictures, right? I walk around. I don't just take random photos, but I take photos of some scene, an object, and from that I can run what's called structure from motion. It is a classical computer vision pipeline that takes a bunch of images, finds a bunch of common points on those images, and tries to match them between the images. And then from there, it can figure out where each of those cameras are in space and some points on the surface of.
I will stop you right there.
Yeah.
I hate the term from motion.
Yeah.
Because and I can see it on I have seen this in the various discussions. You have to actually stop, or originally you had to actually stop, not to be moving when you were capturing the data.
Yeah.
Okay.
I
So
think what they mean though is there's
is
motion, as
really-
in there's been movement of the camera between shots. So there has to be some motion component, or else it's just structure from a single spot. Yeah, marketing is bad in computer vision. But an important note here is, and if you go back and look through all my conversations with the experts, you'll find out that actually those SFM points don't even need to exist. We can start straight with a random cloud of points. We can start out with no points and create a scene. We just need pictures and their poses. When I say pose, where they were in space, in 3D space in relation to each other. But having these points, it says initialization, what we're doing is we're taking these surface points and we're saying we're going to convert each one of these to a 3D Gaussian splat, which is those little green blobs. And then from there, we're going to use this basically circle of process where we're going to take those splats. At the start, there may be 10,000 blobs of these 3D Gaussians, and then we're going to start to change them and move them and duplicate them and remove them until we match these camera photos. So what we're seeing here basically is, okay, you got these splats, and then it's going, those are 3D. Then we're going to what's called projection.
Yeah.
So like when you take a photo of the world,
this is important. In the stage of Gaussians, these are three-dimensional, right?
Yeah. So when I take a picture of you, you're a 3D person, right? You're not Bart Simpson. You're not flat. Take a picture of you. You're 3D. When I take that photo, I'm mapping you onto a 2D piece of paper, right? Or I guess a 2D image on a screen. That's what basically that projection is. So it's going to take one of those camera pictures. It's going to project that 3D splats onto that. Then it's going to go through this says differentiable tile rasterizer. Basically, what it's going to start doing is it's going to then say, okay, looking at that projected image is going to then take those Gaussians and it's either going to duplicate them or change their shape, or it's going to remove them and move them around and rearrange them over and over until it matches that photo from the different locations. So if I have 1,000 photos from 1,000 different locations, as it's running each iteration, it's looping through the photos and morphing the Gaussians. It's just kind of like moving them around, duplicating them, removing the big ones or the ones that are close to being invisible until you've done your best at matching the appearance of your scene, of those images, when you are then rasterizing. When you're taking photos of every one from all those different scenes, you're trying to make sure the scene looks right in every single photo. And you do this 30,000 times, you end up with this really lifelike scene by just rearranging these Gaussians to a state that looks just like a photo when you take a picture.
Okay, so in simple terms, basically from those Gaussians or the blobs, we are basically, with the projection, we are creating the 2D splats, which are in different.
You're just taking a photo of the splats. Just taking a photo of the 3D splats.
Okay, so from each and every Gaussian, there will be only one splat, or it will be a multiple different splats?
A splat would be like a Gaussian would be a splat. To me, like, so that was the other question I think you had from Michael. Like, so a 3D Gaussian it's an ellipsoid. It is so A point. So, Michael, what is in a point cloud that you get when you go take a LiDAR scan? What information is stored in that point cloud, would you say? I'm asking you questions now.
Yeah, you have coordinates, you have color, you have intensity.
Okay, so when you have a 3D Gaussian, you have a little bit more information. You have an XYZ, so there's like a centroid location. So what's the center of that Gaussian? And then you have what's called covariance, which is a term you don't really need to know, but know that like one of these Gaussians could be shaped like a football. It could be shaped more like a basketball. It could be shaped more like a really long spiky lance, like a javelin shape. So they can be stretched out or they could be more round. And that covariance is basically just a bunch more fields that explain the shape of that Gaussian. So we can make these different shapes to try to match the scene. So like when you have an edge of a building, you're going to have these really long, thin Gaussians because it's like it'd be ridiculous to try to reproduce a flat edge with a circle. It'd be better to do it with like a long, spiky Gaussian. So basically, it goes through that process. And then with also in the Gaussian, you have an opacity value. So some of these are almost invisible and some of these are really dark. And then you also then have your color encoding. So like as you move around, what does it look like at different locations? So it can look blue or more light blue or white from different, if you're looking at like water or something, you might have some reflectance. So it might change a lot of colors. So you end up having these kind of a point cloud, but it's got different values than your LiDAR point cloud or a point cloud you get from photogrammetry, because it's just trying to describe the shape of these blobs or ellipsoids. And so basically, this isn't a great photo necessarily, but it's just going to go through this over and over and over until it matches your scene. So that's 3D Gaussian splatting. 3D Gaussian splats are just what I explained. It's just those green points. And if you align them all in a really, if you align them all using this process, and then you get a good viewer that will sort these and overlap them in the right way, then you end up getting this scene that looks lifelike. But it's a one big illusion. I mean, nothing there is reproducing any sort of surface, any sort of, that the accuracy is achieving here. There's nothing about making sure these points are aligned to a surface or represent any sort of geometric shape. It's all about making sure you match the appearance of each photo. And that's all we were caring about in this cycle, at least with 3D Gaussian splatting, just the original version.
Okay, during the processing, you are getting also the sparse point cloud.
That's kind of like a pre-processing step. So that's just like one of the inputs that you get to start. And the minute you put those sparse points in, or if you're using like an XGRIDS scanner, I don't know exactly how their process works because it's not like there's not open code you're looking at, but I'm sure they initialize off of some points that they're getting from their LiDAR scanner, that SLAM scanner. But in the end of the day, that's just a starting point. So if you have a really good dense point cloud, you will have these Gaussians probably already somewhat aligned in a more dense and closer to reality way. And you'll get to a really good looking result faster. But you don't have to start with the dense point cloud. You can start with the sparse point cloud. You could actually just do a random point cloud. You could just throw a random 10,000 points in 3D space at it and say, start with that. And it will work from those. A lot of times it takes a lot more iterations and longer to train it to get it to look good, but you don't have to really have points on an actual surface.
Mm-hmm. I have seen you posting several videos also about 2D Gaussian splats. So what's the core difference?
Yeah, so these are 3D, so they're blobs. They're ellipsoids. They're shaped like I like to say they're football shaped or basketball shaped. When you have 2D Gaussians, they are not shaped in a 3D. They're 2D. They're like circles. They're actually like flat discs. And so one nice thing about that is the original 2D GIS was like a surface aligned 2D Gaussian splatting. So what they do is they are using some geometric surface and they're mapping them to those surfaces. So the nice thing is, instead of trying to represent like a flat wall with a bunch of round shapes, you get these nice flat disks that you can overlap on top of each other and align them to surfaces. And in some ways, you get a better result, or there's like trade-offs. You have now a bunch of flat disks. It's easier to then perhaps get these sharp surfaces like a wall, to get it to represent easier or better or more accurately than if you use a round, round shape to represent a flat surface is tougher. So what you end up with 2D Gaussians is just a different type. It was called primitive, a different shape to use to represent this world. And yeah, your surface lining. So when I was showing some examples, when I was experimenting with it, I was showing like a 3D reconstruction of a scene, and then I was showing surface normals, which is basically just showing here's the surface of a building or surface of an object. The normals are just telling you like what direction is pointing out, what is the front of that, and so then it's attaching all those 2D Gaussians to those surfaces and knowing which way is pointing out, and so it's better able to align those 2D flat shapes to this 3D scene. So it's to me it's a good way of mapping like structures or things that have a lot of flat surfaces to them.
I know that we discussed also with Michael the triangle splatting before, and you had some different point of view on that. Could you just explain from your point of view what does it mean, the triangle splatting?
Yeah, and I have a really good video on it on YouTube as well. So if you really want to go deep, but basically, so I'm trying to bring up another visual for you that I realized I didn't send you, but let's see if I can find it. Oh yeah, here we go. I think I can share my screen on this. So,
yep.
So I think Michael had said, or like I could just say it too, is we don't know what exactly is going to be the perfect way to represent a scene as a radiance field, or there is probably no perfect way. Let's see if I can just share the my screen on this, but there is a project called convex splatting, and let me know if this is showing. Oh, it is. Okay. Yeah. This is convex splatting, and this came first before triangles. And if I zoom in on this part of my screen, we're basically now, instead of representing with these 3D Gaussians, we're using convex shapes. So imagine instead of each thing being a blob, and then it kind of has this fuzzy appearance on the end, because a 3D Gaussian splatting is dense in the middle in appearance, and then it kind of feathers out. Imagine each shape could be a convex shape. So it could be this rectangle, it could be a perfect circle, it could be almost like these more complex primitive shapes where it's maybe thinner on one side and more rounded on others. And then we could also say that the Gaussian, instead of a Gaussian, these shapes could have a really hard, rigid edge. So like here's the rectangle, right? There's no Gaussians fall off. There's no fuzziness to it on these two, but these do. So what it's saying is we could represent this whole scene using any of these shapes. It could be hard edge, they could be the smooth edge. And the problem when you're trying to reproduce the visual of a scene like one of these, a good example is this truck down here. You end up with these boards on the truck, and they got really sharp edges. And it feels silly then trying to reproduce the edge of a sharp edge with a fuzzy round shape. It just doesn't make sense. So they said, well, what if we use a not fuzzy and a hard shape, like a rectangle? If you want to reproduce a big flat wall, you could do it in a few rectangles versus a million round blobs. And so they came up with what's called convex splatting. And it uses fewer of these shapes to represent the scene, and it can even look better than using Gaussians, these blobs, because then you're able to optimize each shape to kind of the structure of each object you're trying to then reproduce. So that's convex splatting. Well, then a researcher said, well, what if we don't use, what is it, 6 points? What if we try this with just 3 points? It'd be less data, and let's just do triangles, but have the same type of properties where the triangle could be really hard edged, or it could be more feathered out like this. And they found that triangles work just as well. So we end up with triangle splatting. So I think it's like perhaps the most superior of the different ways you can reproduce a scene, because you're able then to match the appearance of each blob or triangle to better, mimic the scene that you see here in real life. Because again, there's in this scene here, you got rounded truck. You can use round objects, and in the background, you got this building with a bunch of sharp edges. That it'd be better just to use a triangle, a bunch of triangles. You can make rectangles out of them, whatever shape you want.
Can you, or is it possible actually to combine those, like 3D Gaussians with triangle splats?
I don't know. I'm sure someone could figure it out. Make them triangle, make them round. That's a good question. That's up to the researchers. I'm gonna stop sharing this. But I feel like the problem with all of this that we ran into, and this was the thesis of my video, is do all these matter? Like at the end of the day, we've all adopted 3D Gaussians into all these different viewers and plugins and in different software. There may be a better way to do it, but it might be that like it doesn't matter because we've all decided this is what the form we're gonna build on. In fact, I think I saw yesterday was that the GLTF standard is looking to standardize 3D Gaussian splats for radiance fields, and it's like once that's standard, there's no going forward. There's no good luck telling everyone, okay, we got to rewrite all our plugins, all our renders to work with triangles. It's just not going to happen, in my opinion, right? Once you standardize on something that's, to me, good enough, doesn't matter. Are people going to go retool everything to work with something better? I mean, we ended up. I think I don't know how old you are, but I'm old enough. I'm not even that old, but I do know the story of VHS versus Betamax. Betamax tapes supposedly were better for film than VHS, but everyone went to VHS, and so we ended up with this inferior product. But that's what the world chose, and that's what we're having here, which is good. They're both good options.
Great. Before we move on, we have one real fan here. Just saying that we are the most lost people that he has ever listened to. So
what are you lost?
Just saying hi to Terry Hammer.
I just need more pictures. Yeah. So just think about it. Every time you look at one of these scenes, it's just a bunch of turbocharged pixels that could be stretched in different shapes and to mimic the appearance of the real scene. And they just found out when they originally did this research and they came out with 3D Gaussian splatting, they found, oh wow, when you look at the scene from what's called novel viewpoints, right? Because what you're doing when you're creating a scene is you have maybe you have 1,000 photos as your source. You're going to match the scene to those 1,000 photos where it should look. Those are called ground truth, where you're trying to get it to match 1-to-1 the appearance of your Gaussian splats to those source images. But they found out that when you move between those images in 3D space, the scene looks still pretty good. It looks really convincing. Like people don't realize there was no photo taken from that viewpoint to reproduce that scene, because these Gaussians just do a good job at mimicking appearance from new angles. Probably made people even more confused there. But
you said the one interesting thing about the triangle splats, that it's just logical to use something different compared to 3D Gaussians when we are working with corners and flat surfaces and so on. This brings me to the topic of accuracy. I know that everybody is asking about the accuracy of 3D Gaussian splatting, but it is actually important thing because it's just my point of view, but the technology as itself, the 3D Gaussian splatting, at least from the beginning, I don't think that anybody cared about the accuracy of surfaces, corners, or points at all, right? So what's your opinion? How do you see it in the current state and in the future? Will this be solved regarding the accuracy of 3D Gaussian splatting, or is just the feature, not the bug?
Okay, I'm glad you asked this question. I'm gonna bring up my screen again. I have a paper ready.
The picture one, you want to bring?
No, I'll just bring up my screen.
Okay.
I didn't have these ready for you ahead of time. Okay, so again, this is another question that bothers me because people ask about the accuracy of 3D Gaussian splats. The same with another thing that bothers me is the question about like where's the
sorry to be bothering you.
like, where's the texture file? There is no texture file. It's encoded into the it's in that it's in those fields within the points that explain the texture or the color of this. But that being said, when we talk about accuracy of 3D Gaussian splatting, it's an apples and oranges to point clouds from LiDAR and photogrammetry. When you're looking at the accuracy of a point cloud from a laser scanner, you're looking at how accurately did it reflect the surfaces or did it capture the surfaces of the real world, right? So you're going and you're looking, you're saying, okay, within a certain millimeter of accuracy, it got where that surface was in exactly in the real world. And so that's the accuracy you look at in a point cloud. From a LiDAR, from photogrammetry, that whole goal is, how do I get this a geometrically accurate point cloud? Now, when I was explaining how you make 3D Gaussian splatting, the first thing it does is it takes these semi-accurate sparse points, these points on a surface, and says, I don't care where those belong anymore. I'm just going to move them around wherever I need them to be to make sure the scene looks right. So within a few iterations, all the accuracy has gotten worse when it comes to geometry, to geometric accuracy, because it just does not care. It'll do what it needs to do with those points to make sure it looks correct. So when you are going and you want to go look at new research in 3D Gaussian splatting, you will find, here is the original paper, you will find there is an accuracy page. There is always accuracy metrics. But the accuracy we're looking here are these three values that are very common. There's some newer ones, I think, coming out too. But this first one is peak signal to noise ratio. Basically, what it's saying is I have 1,000 photos that you use as your ground truth, right? And then it reproduces your scene as a Gaussian splat. It's going to take that ground truth image, and then it's going to take that picture, a picture of the Gaussian splats at that same point, and it's going to compare those two images, and it's going to say, like, how close are these pixels in color and intensity? How well did we reproduce that picture as a Gaussian splat? And it'll score it. And the higher, the better the score, then the more accurate you will say, like, or how faithful did we reproduce this? Then there's this SSIM, which is a structural similarity metrics, which is instead of looking at your pixels, it's looking like, did we get the edges and the structural similarity of the scene correct? And again, we're trying to score that and see, like, how did we get the general shapes of the scene looking right? And then there's this last one, which is called, I don't know which one stands for, but it's LPIPS, which is basically saying, how much does a human perceive this scene to be real life? Like, how well did we fool someone to think they just took a photo of the actual scene? This isn't actually 3D Gaussians. And so again, those are the metrics that we're comparing. So when you're seeing accuracy of 3D Gaussian splatting, there is an accuracy. It's how well we made the scene look like it does in real life. So that's where I think Michael was saying, like, you'll have an invisible point cloud layer behind this where you can easily toggle on and off different layers of data. And so you can still preserve your original point cloud that you initialize all the training off of, and that can live in the same coordinate space. It can be right there with your scene. And then just think of 3D GS as a visualization layer. That's all it is. And so when we're coming out with new methods, they're trying to get it to look more and more accurate, not be more and more structurally perfect, because that goes out the window unless you have some special project that's trying to achieve that. I think 2D GS might be more geometrically accurate, but again, still, it's not perfect. You know, like, you have a circle, so you're not going to put points right on the very edge of a building because they're going to be projected out in a circle. So that centroid isn't really on the edges of things.
So basically, the technology wasn't meant for that. Like, if you need accuracy, then go with precise photogrammetry, or use LiDAR, or use TLS, whatever.
Right. There's all these different viewers now that'll let you put them all in the same software.
Exactly. Like, 3D Gaussian splatting is not here to replace everything else, right? So it's just another layer, another way how to see reality and how to reproduce reality.
we're already doing this. If anyone has used like a BLK 360 scanner where you end up with like these 360 images and you can then like measure on the 360 image, it's really measuring on not the image, it's measuring on a 3D layer underneath that you're looking in the viewer on their software. It's just got like it's using the point cloud from it turned into a mesh, and then you're just measuring on the mesh. But
if I understand it right, you are basically getting the coordinates on every pixel. So you are looking at the image, but you are still measuring on pixels with different coordinates and values.
Yeah. So that's what we have here, where we could have the scene where you're looking at a 3D Gaussian splat, and you could be measuring on it, but you could say don't measure on the actual splats, measure on.
So basically, guys, if you are buying a car, you don't care about how deep it can go into the water.
Yeah,
it's not meant for it.
Or what's great about I've been experimenting a lot with the portal cam, and it does get a good SLAM based point cloud. We're still not probably at the same accuracy as like a TLS scanner, but you end up with this point cloud, and their collision layers are always so good. And I don't know what they're doing. I think Mindy's on this. She could probably tell us one day, but I'm pretty sure that they're using that point cloud to figure out where the collision is, where the surfaces are, not the 3D GS, because you already have good geometric shapes from that scanner. There's no reason to then use the points from your 3D GS to figure out where the collision layer is. I
think that's exactly what they are doing. Just using a hidden point cloud for measurements.
Yeah,
and when they are taking this into Unreal Engine or Unity or wherever, they are just using the 100% opacity on a simplified 3D mesh, and that's it. You have collisions there, right? Yeah. So even if we use workflows for producing 3D Gaussian splatting, there is like the easiest solution is to produce also 3D mesh in a photogrammetry software. You already have your registration, or you can run the registration or alignment in a photogrammetry software, then take that alignment, put it in a 3D Gaussian splatting workflow. So just do another step if you need the accuracy, and stop asking about the accuracy of 3D Gaussian splatting, because it doesn't make sense.
You have to highlight David Boardman's comment here. Splats for show, points for dough. He's been used as points for dough, meshes for show, mesh for show, points for dough, back before we had splats. It's so true. In the end of the day, like the visuals are just the eye candy. Like if you're building a building, what's most important is again, you come from that AEC world, right? It's like you want to know if pipes are going to collide. Well, you're not going to figure that out off of some visualization. You're going to be going to those really good surface points, and you want to be measuring off of those, not off of some visualization layer. That just helps give you better context and orient yourself. Because at the end of the day, people really just want that data. Unless you're using it for training some visual perception AI or something.
I'm probably offend more people at once, but I would say it's like difference between architects and engineers, right? Like architects don't really care how you're going to build it. We just want it this way because this looks perfect. Right?
Yeah. Yeah, you figure out how to build it. I just did the pretty drawings. So So there we go. There's my soapbox on accuracy. These are not accurate to geometry, but they can also live. People have also asked us, well, what about the GPS points? And I want this to be aligned in the world coordinate space. It can. There's no reason why it can't. The original project was not concerned. Most of the researchers are not concerned about that sort of aspect. They will build these projects. The first one was, could we even do it? And then from there, it's been just iterated on making it look better. So no one's been thinking, but let's make sure these points got the XYZ coordinates are initialized at the start, and that if we move points, it's still living in the same coordinate space. It does this transformation. It does these things where it changes all the values of your point clouds to optimize to go fast. But you can, I believe in like Gsplat and these different platforms, you can change the default to say, no, preserve the coordinates of the original splat. So when it starts moving everything around, we're all still in the same space. The thing is, most people aren't really getting high quality scans to have good, coordinates anyways. They're using an iPhone. Well, I've seen iPhones bounce off walls and put you across the street. And so you want to make sure if you care about locking these in on good coordinates, you have a RTK or something like that when you're capturing your initial points.
Right tool for the right job.
Yeah.
Let's move on. We have a second topic here, which would be Gaussian splatting in a simulation.
Oh, yeah. We got my visuals now.
Are you sharing?
Okay, I gotta start this. I was originally not excited about 4D Gaussian splatting. People keep wanting to ask me questions about it. They're hard to. You need for a 40.
I removed you. You were boring. I removed it.
Yeah. Well, for 4D Gaussian splatting, you need a lot of cameras. It takes a lot of processing power. It's just something people aren't going to do. But I found that 4D Gaussian splatting or dynamic Gaussians are really helpful in simulation when it's all synthetically generated, and you don't worry about having like a volumetric capture studio. Because people keep saying, when are you going to do a video on 4D Gaussian splatting? Well, I don't have a volumetric capture studio. I don't have 20 GoPros. I don't also want to spend 24 hours of my workstation machine just processing that data to produce 30 seconds of 4D Gaussian splats. So simulation, though, has caught my imagination on how they're useful. So I don't know if you wanted to show any of those videos, or I can.
Which one?
I think I numbered them. Show the one that's like the number one, has the one at the start.
The Tesla one?
Yeah, so this scene is Tesla's autopilot simulator. So if there's a unique thing that happens in the real world, they're able to queue up that scene and then like play it out in a simulation world. And this whole entire scene here is all synthetic. If you look at the truck on the right side, you'll notice the text looks like gibberish. Or if you really looked at that Ford emblem, you notice it actually doesn't say anything on there. However, this whole scene is 4D Gaussians that have been basically predicted using Tesla's what's called world model, basically their model that predicts what scenes would look like if it plays out. Now, the great thing about using Gaussians for this is you create this 3D scene that you're able to then to virtually drive through, and everything will stay like geometrically accurate because it is a 3D scene playing out in 4D. So the pixels are moving like they would in real world. But in the end, you end up with this photorealistic scene. And then if we know how Tesla works, it's all trained on visual data, right? So you want to put a Tesla down a street, it doesn't use LiDAR or anything like that. It's just using all visual data. And from there, then it's deciding to make actions. So they're able to then replay these scenes and see how the Tesla would react. Because they can then say, oh, this was an interesting scene, play it out. They can change variables. So I think if you go to the next one, you'll have a next idea. There's a couple simulations I show.
Yep.
Some of these have sound, so I don't know if those are going to play or not. So this is their real-time version that they showed it's called NeurIPS, which is a machine learning conference, where you can literally just drive down the scene. So they could queue up a real-life scene and then just drive. It's hard to see the steering wheel. Actually, the next video is me doing it myself. But you can just drive down this scene and play it out. And so this is just Gaussian splats. And this is an optimized version to run in real time for like demo purposes. But we saw this first version, everything was perfect. It looked like reality unless you really looked at it really closely. But so here, then someone can, things are starting to go downhill as they go further in. But you can start to replay these scenes and then train your Tesla to say, oh no, you shouldn't be doing that action. You should be doing this action instead. So that guy just went across the double lanes. He's driving into a house, things you're doing that aren't good, but it can start to learn from people driving around. So this is why I like Gaussians for simulators, is because everything stays consistent. If I turn my head to the left and then turn it back to the right, things don't just magically disappear because they were always there as a 3D Gaussian. Does that make sense?
But just to be clear, what we're seeing right here, is it actually like reconstructed the real scene also with cars and with all the movement, or is it the 3D Gaussian splatting splats scene and then just added cars and
Yeah,
Is the combination or
it's all everything in that scene was Gaussians.
okay?
And it's using real-time frame generation. So they're running this on a really big server somewhere, streaming it to that computer, and it's doing real-time frame generation. So it's like real-time predicting where those Gaussians are going to move. And it's really crazy what they're able to do. Not something you're going to be doing on a laptop or your desktop. But it's been great for being able to train. It's called car policy. So policy is saying, like, what do you do if a ball runs out in front of a car, right? It's going to want to brake, right? It doesn't want to run over the ball. And then so they can redo that scene 100 different ways to make sure that it does it every time. Then you can also start to train on logic to be like, well, then maybe wait a little bit longer. If a basketball rolls across the street, there might be a child running after it next. So don't accelerate the second that ball's passed. Things like that. And so they're able then to bring up all these near misses and all these different anomalies in their data and replay those scenes and have a human operator even then go drive through that same situation, and it'll learn, okay, well, that's what I should have done. And it's all using Gaussian splatting for the scene generation.
And you can probably also train different versions when you're driving a small car compared to when you're driving a truck or
yeah,
yes,
exactly.
Ram, right? So,
yeah, I had another one. So if you bring up the next video, it's called like it's like introducing MCD.
I changed the input.
Oh, this one's me. Okay, this is me driving it. So I actually drove it at Neureps myself, just to show you that it was real. So I see all these tech demos, and I'm always like, I've never seen it in person. I'm able to check. They said I could go wherever I want for several minutes before it would have to be reset, before it can no longer reproduce the scene. So there I am. I'm trying to drive and film, so it's really hard. But if you look closely, you'll see the trees aren't perfect, but it's all Gaussians. Even those cars in the background driving are Gaussians.
How was the scene captured? Did they use like multiple cameras, or was it from 360 or?
They start with just all the cameras that are mounted on a Tesla. So they initialize it. So at their talk, they were saying if there's something of interest that their AI will then grab and say, this is something you need to look at, then it trains that initial scene off of all the different all the car cameras, and then it trains from there. Which is kind of like a synthetic 360 image because it's got all these cameras mounted on a Tesla. That next one, I have another one that it kind of explains a couple things Michael last 2 weeks ago talked about. Oh, not that one. There's another one that should say, like, I can bring it up if you want.
Do it.
It's a MCity parallel domain replica. So there's a company called Parallel Domain. Hopefully they're excited I'm talking about them on this, but they again are like a driving simulator company, and they originally were making what's called procedural generation. They could create scenes, had 3D artists creating, streets, highways, things like that, and it took a lot of time. And they started using 3D Gaussian splats again to reproduce the scene because it was much easier to drive down a corridor with a 360 camera and recreate it than it was to then have a bunch of 3D artists doing it. Let me know if you can't pull it up. I can.
You're not sharing yet, so I don't know if you're
I can share it. Here. Oh, yeah, that's it. So this is, again, I don't have music, so probably have to stop it. This is there was a question last week or 2 weeks ago about, is there like a size limit? These guys like mapped out a huge portion of Michigan, not Michigan, was it Detroit, as Gaussian splats. And then you'll see if you play this video, I guess it's my video, sorry. If I play the video, volume here, you'll see that you can map out huge territories. And then the cars, a lot of these cars were put in there as after the fact. They are basically meshes, right? But the cool thing about this is then they can simulate like their LiDAR and their sonar returns. They can what I said, perfect annotation. What's great about that is if you put a car in there, 100% that's a car and what it's supposed to look like. And so then when you're training these systems, you're already saying, I know, you're telling exactly what everything is ahead of time. So doesn't have anything wrong. So that's kind of an interesting thing about this is that again, this is not a like Tesla where the whole scene's moving. They added meshes and all sorts of other assets to populate the scene, but then they could go and capture this whole take a 3D artist a long time to capture all this. And then people might say, well, this isn't 4K perfect visuals, but I also have to remind people that the camera sensors on like self-driving cars or robots are like 640 by 480 resolution. They're not looking at 4K at the scene. That's too many pixels for it to real time work with, and it doesn't need to know. It just needs to generalize. This is a car. This is a ball. This is a an obstruction, and it runs from there.
But shouldn't we expect, especially with the approach of Elon Musk, and we know that he's like generally against LiDARs. He just wants everything to do based on visuals. So shouldn't we expect the resolution of cameras to be at least like a human eye, or like? I know that this is heavy on a computation, but just for a general public to trust the technology.
Well, that's a good question. I mean, his theory is that we're driving around without a LiDAR, so our brains or neural networks have figured out what the scene looks like. But also, when you're looking around, think about how much of your vision is actually in full focus. It's a really small part, but you still are like paying attention to things on the edges of your vision that aren't even in focus, let alone, you know, like I wouldn't say they're in 4K. So I guess I don't know the best answer to that, but my thought is probably these will get better as our software gets faster and is able to consume higher resolution data, but it doesn't have to be. Doesn't have to be 4K or 8K. I mean, you can see a car way off in the distance, and it's not very big, but you still know it's a car and it's coming at you. And there's not many real life pixels on that car if it's far away. It's just like a dot in the distance.
Yeah, but it's a similar argumentation than when you say as long as automatic cars kill less people than regular drivers, then we're okay. It's like logical, but I don't know if it's good enough argumentation for general audience, right?
I mean, we're terrible drivers. I got in a car at like 1:30 in the morning after I was at a pub. And let's just say I got in a Waymo in Mountain View, and I felt way safer with a car that doesn't get tired than at 1:30 in the morning with some Uber driver who maybe have been driving for 8 hours, 9 hours. So
there is this old saying that if you can imagine the average driver, which is pretty weak, then just imagine that half of the drivers are worse than the average one.
Yeah.
Right. Yeah. So you can just imagine like where are you moving actually when you're driving your car. So yes, I agree with you on this. I'm on this with you that I would much more trust the self-driving car than.
Yeah, I mean, it'll be best when they're all self-driving cars. The problem is that we got messy people still out there, and so I don't know. That could be its own podcast. I don't know the right answer. All I know is that when I took my first Waymo car ride not that long ago, I was shocked at how much it drove like a normal human as far as aggressiveness. And I didn't feel unsafe, and I didn't have to talk to anyone in the car, which is a big selling point. So,
is it a different? I haven't tried either of those. Is it a different feeling when you are driven by Waymo, for example, when you are sitting at the back seat and then just trusting the technology that
it is weird at first.
Whatever you need, compared to Tesla when it's in a self-driving mode, and you're actually sitting on the driver's seat, but you're not driving.
Oh yeah, I think it was a little unnerving in the Waymo at very first. But there's a button you can click, tap that'll automatically put it into like pull over to the side of the road mode. So I don't know. It'll take some time. I mean, I'm still uneasy in my Kia that just does lane keeping. Sometimes I still feel like I have to take over, but I don't know.
Yeah,
I do have like 35 minutes, so I want to make sure we don't run out of time on this.
Do we have any more content or videos regarding the simulations, or are we going to jump on
Here, I'll show a couple more. If you throw on my screen, I'll just show you. I'll show you a couple more that I think could be interesting.
Okay, so I will share your screen right now, so people will know what you have in your folders.
Yeah. So this is another way of using simulation with Gaussian splat. So this whole scene here is Gaussian splatting of a robotic arm doing a task, and then there's like all these different variations. It's not a really good video necessarily, but what it's doing is, if I just pause right here, we're taking a real example video of this robotic arm doing what it just did, and it's able then to turn it into a Gaussian splat, and then you're also able to feed it what's called arm state, like robotic state data. So I can just say, here's all the different ways this arm can move. And then it can replay the scene and do a bunch. It can do it's called reinforcement learning. So it can start to learn how to do all these tasks. And instead of having to have like a mesh, I don't have to spend time like rebuilding this whole scene as a mesh. And as you know, like you don't have to be a 3D artist to rebuild all these shapes. And then it can just train on the visuals, and it does it all as Gaussian splats, because it does a pretty good job at recreating things as Gaussian splats. So that's one way we're using it in simulation. I just want to show that it's more than just cars. There's another one. This one will be much closer to like what I'm doing at work. This one, again, where you actually have a simulator and you don't spend all this time making it look good. And then you take a Gaussian splat and you put them together in what's called splat sim. And then it's able then to basically map the scene onto that low quality simulation. And that way it helps, like if you have what's called perception system, it want to make sure that your robot is paying attention to the right things. And not like the table grain. And then so you're able then to replay all these different scenarios, and I don't have to then go create this scene from hand. I can just create a Gaussian splat of the scene and let it take over. So I feel like this is really interesting, because it's just going to speed up how quickly we can get robots in the real world. Here's one more. This is a robot it's called Isaac Sim, which is a simulation platform from NVIDIA. And yeah, it's dancing, it's moving around. But this whole scene was captured using Nurek, which is NVIDIA's open source Gaussian splat package. So I could go take a bunch of pictures and then of this room, and then it'll run through this pipeline, turn it into Gaussian splats, and I can get a high quality mesh out of it for collisions. And then I can start training this thing to navigate in this. So I can put objects on the table, things like that. All you need is cameras and their open source software from NVIDIA, and you got yourself a whole scene that works straight in their simulation software.
Since you mentioned the NVIDIA, if I'm not mistaken, you are also in an ambassador program of NVIDIA, right?
I'm in the what?
Ambassador program of NVIDIA.
Yeah, I'm a creator. I don't know exactly what I am with them, but yeah, I do a lot with them. I also worked for Lightwheel, and Lightwheel is one of their Inception partners. So, like if you go to like the last few keynotes, you'll see Lightwheel is featured in their opening keynote montage of companies that are doing interesting things. And we provide high quality data for simulation. So, you want to train a robot. This is like so okay, let's say your company wants to build the matrix for their robot to learn in. And remember in the scene where they're in just that white room in the Matrix, hopefully I'm not losing all the young people who've never seen that movie, and they're like, cue up this scene or cue up all these guns or whatever, and these things disappear. Imagine we're the ones who created the scene and created all the different assets within that scene, and they all have to be highly physics accurate or else nothing works, right? Can you imagine if you picked up an apple and it had no weight, or a glass of water and when you tipped it, like nothing, like the water floated out as opposed to spilled out, and the weight didn't work right, and all the friction wasn't correct. What we do is we create these really high quality assets that have those physics properties built in. We actually even test in real world. We will take like a cable and we will bend it, and we will take the force curves of the bending and spring back of that, and we'll simulate that in our matrix or Omniverse, and making sure that they exactly replicate in the simulation as they did in real world. So that's what I do at Lightwheel, is I help people figure out how to best use these data streams for training robots. And I say a robot, that could be your car, self-driving car, that could be a humanoid, that could be a couple arms folding laundry at a laundromat. We're seeing all sorts of use cases popping up. But there's one more video. So this is how we're using it at Lightwheel. So Marble is a world model, and it's able to take, so it took a 360 photo of this hotel room. And then you can throw it into Marble, and then Marble will create a Gaussian splat of the scene from one image. And I can move all around. So it uses, and then here we go. Here's our high quality cloth asset from Lightwheel and a robot, and it's now learning to fold. And why this is interesting is we still have technical artists on our team who are building these scenes to train a robot on. We need surfaces, we need tables, we need rooms to put them in. You can't just train them in a blank room, because in real life you'll put that robot in a real room. Well, we can now shortcut all the time it takes to basically build that room. We can use photogrammetry, but again, even that takes longer. We just can throw a single image or a short video into Marble, which is a world model from a company called World Labs, and then it'll just pop out this scene, and it will be geometrically accurate. It does a pretty good job at reproducing areas it didn't even see that was occluded, just because it understands real world scenes. And then we can even change things.
Why is it important to train a robot in a real world or the digital replica of the real world? Is it because it is learning to understand the world, or
yeah, there's a few things. Like, you don't want to make sure there's like these attention networks within a robot, right? So as it's working along doing this thing, there's lighting changes, there's people moving around, but then there's also the room itself has all sorts of objects. Like, I guess imagine if this room had a bunch of other, like, let's say I didn't use this perfect room and I used my like my daughter's messy bedroom with clothes all over, and I said, and the instruction for the robot is fold the shirt. Well, what do you do if there's like 12 shirts laying on the floor? You want to make sure that it's paying attention to the one that's supposed to be and not the other objects in the room. And so you just want to give it a lot of different contexts to work in and a lot of different places to operate in, and learn that, okay, only focus on things that are close to you. Stop paying attention to the things around you that aren't important, and be more context aware.
But it's not only
amazing. It's
not only for the geometry or navigation. It's also for understanding, like, okay, this is bunch of clothes, this is some cupboard, this is some sofa or whatever. So it needs also to understand the scene, not only to geometrically navigate, right?
Right. And so there's tasks it's doing in the scene, and then it needs to navigate around the scene. So it might be given it several tasks in a row to do, and the next task might not be right in front of it. So now it's got to figure out how to get around the room to the next task, find that task, do that task. Maybe it's go find the red shirt on the floor and put it in the laundry basket, maybe because this is a housekeeping robot. So the faster I can build a bunch of different environments and test it to complete tasks in different environments, the better we can evaluate. It's called a policy again. It's called a policy. Like, the task that we're telling this robot to complete, can it do it successfully in a high amount of variations of scenes?
I wanted to ask also about the Omniverse, whether the 3D Gaussian splatting is already like implemented in the workflow of Omniverse.
Yeah, so they have what's called 3D GUT, which is 3D Gaussian Uncentered Transforms, which is an open source project they have. But within that project is a converter that will take any 3D Gaussian splat as a PLY file and convert it to their USDZ format. So then it'll just work inside their simulator. It's kind of handy. So that's what you're doing here. I'm creating this Gaussian splat within World Labs' Marble. That outputs a Gaussian splat file, and then I just use 3D GUT to transform it to work within the Omniverse. And you could create that own pipeline. They have now an API for this. You could have it all done on the back end. You wouldn't have to be manually doing anything. You could just create your own pipeline. So that's something we're doing. Here's one more. Here's my kitchen. This is from World Labs. Again, this was from a 360 image. I just wanted to show how good it is. But again, if I start to measure surfaces, I want to see how perfect this is. You see, some things fall apart. You'll see it didn't do my kitchen island because I didn't see it. They're getting better at some of this.
It's from a single image, right?
Yeah, it's all from one 360 image. You can see where my tripod was on my thing. So it's interesting, but again, it's not going to replace going around with like a portal cam or going around with a really nice camera. You're going to get much better, more accurate results. So what are you looking for? World Labs is great if I want to put out 100 different variations on the same room, because you give it a text prompt too. I could change the colors of the cabinets. I could add different objects. What it doesn't do is make an exact replica visually. That's where cameras or the SLAM scanners are better. There's a couple more things I'll highlight then. And then so with these world models, we're able then to predict also. They do what's called frame prediction. That's what like Genie 3 is doing, right? So we talked at the start, you're moving around, it's predicting like what the scene looks like as you move around. Well, this is called Gen 3C. This is kind of the same deal. I'm taking 5 images of all these different scenes, and it's able to recreate this whole entire output. And because it's what it's doing is it's basically creating frames between those 5 frames of what everything will look like. And why is that important? Well, I guess my next video. When you start to get really good predictions, you can start then to fix things. So if I capture these scenes, I don't have enough input images, it's able then to predict those what we call corrupted novel views, right? I didn't get a good picture here. Well, it can predict what that should have looked like, give you a fixed novel view, and re-inject that back into your training. So let's say I got only 100 photos of the scene, and as I'm moving around, things start to fall apart because I didn't get enough good photos of that part of the scene. Well, what this does is it says, okay, well, that part didn't look so good. We're going to predict what that looked like using a world model. You should kind of understand what the world looks like when you move around, and then it'll fix it or give you more degrees of freedom than you originally had. And so this may have been a point a couple weeks ago about using their fixer model, where basically there's just ways that we're now able to, here's an interesting one where you could literally drive down a street and then say, move over 6 meters. You never saw anything from 6 meters over, and get it to turn out to look pretty darn like it would 6 meters over, even though none of your footage backed that up to look like that. So AI is going to be, I think, a big role in a lot of this 3D Gaussian splatting, just because you're going to then able to fix things that you made mistakes with and capture parts of the scene after the fact. You can say, okay, predict what that looked like.
We have actually a question regarding the physical AI from Mindley. So do you think physical AI will become a new direction for 3D GS, or that 3D GS will serve as the foundation for world models?
I think it's kind of both. Nice question, Mindy. I feel like 3D GS is a great way to, again, it's a great medium for displaying the world. That physical AI can take advantage of. It's just going to say, oh, okay, instead of using pictures or video or point clouds, which like machines don't necessarily understand, it doesn't look right if you're using cameras, perception models, we're just going to use this great 3D GS medium that looks right and is structurally correct. It's approximate structure is correct. But we can also use 3D GS to train. It's like a cycle. You can produce these, and then we can use it to train the physical AI models or world models. So, but when like Lightwheel, we help companies train world models. A world model is basically an LLM, it's like ChatGPT, but for the world, and it's trying to predict what could happen in the next few frames, or how would the scene play out. But it has to conform to world physics and scenarios, and it can't just be like it can't be like you see these like Veo 3 where you can have like I don't know, a cat on the moon wearing a spacesuit playing golf. That could never happen in real life. World model has to say no, that can never happen. And so we have to give it a lot of good physics accurate data, a lot of good real life high quality data, and 3D GS I think is just one of those data streams that might help reinforce these world models.
It's very similar to language models, right? Like for example, the scene you were showing before from 5 images with the Gen 3C.
Yeah, this is open source from NVIDIA if you want to play with it.
The goal is to predict the best possible option, what is actually happening there, right?
Yep.
Because you have no idea what's actually there on the second frame, which you didn't took with the camera.
Yep.
But the goal of the AI is to predict the best option. So it's similar to language model. Like it's only about the prediction of or picking the best possible next word that is following the previous idea and previous words.
Yeah. So ChatGPT evolved fast. They scraped the internet in every book on the planet, right? Because it's taking a token. It's taking words and it's turning them into tokens, it's breaking up into little numeric chunks, and it's predicting what's the most likely words to come out of a question, or when I ask it things or talk to it, it's going to predict what I think is the most plausible answer based off of a bunch of math. And so it's pretty easy to train these. Not easy, but there's more easily available data, all the text on the internet, pictures, things like that. It doesn't care if a video is accurate or not, if you're training even these video models. But when it comes to training world models, everything you need you need more than text. You need visuals, but you also need to make sure it's physics accurate. You need annotations, so descriptions of what's happening in that video. You need to give it, if it's like robotics geared, you need to make sure you're giving it like what's the hand tracking, what are the fingers doing, all that. So you end up with all this information that you need to add on top of these. So it's going to take longer to train these because we need to go out and purposefully collect data for them. And the world's almost infinitely complex. So, we scrape as much data as we can. This is built on NVIDIA's Cosmos, which is their world model. It's open source. You can go use it today. It does videos and reasoning output and style transfer output. It works, but you will quickly find what they didn't train it on. You'll say, okay, I want to predict what a robot arm will do in the scene. In the season was called a gripper, like a pincher instead of fingers. And the gripper might start to morph into fingers. You're like, oh, why is that? Well, they trained it on primarily robots with fingers, things like that. And so you'll start to say, oh, we got the physics wrong on that just because I don't have enough context yet. So,
okay, I think we already went naturally from simulations into world models.
World models, yeah.
Can we just in general say what it actually is, the world models?
Yeah. So basically a world model, again, I kind of said what it was. So a world model is basically, think of it as like an LLM, but instead of predicting words and text and pictures, is predicting what is happening, what could happen in the world given like an input. So I could say, here's a picture of a car and there's another car coming across the lane. Predict what's going to happen next. What is the next plausible world state that could happen? And so that is one way a world model works. So it's just predicting the future. So Genie 3, it's trying to predict each frame. What could actually happen in this frame? What is the next thing? You got to make sure it's physics accurate, things like that. Or World Labs is Marble. They're inferencing just to put out static scenes, but it's saying, given this input picture with the lighting and everything, what would the scene look like as a 3D model? So it's basically taking all of the corpus of information and predicting what the scene looks like in 3D. Okay,
just the disclaimer. I know you already mentioned it, this answer, but I needed a cleaner version for my YouTube shorts. Okay, so
yeah. So world model is basically a prediction engine to predict future world states, what the world would look like.
Perfect. The following question is: do you think, or maybe how it's actually working? Is it working like pixel by pixel, or is it actually analyzing the scene with the objects and what's connected to what? Like, how does it work on behind, or is it just the black box and nobody knows?
Oh, I mean, it's all just math prediction. That's a bunch of math, but like when you're training it, there's things that we're learning that you have to make sure that it's paying attention to the right data. So there's projects that are saying, when you're feeding it a bunch of data to train these, there's a bunch of, let's say I give it 10,000 hours of motion data of like waves and just random videos. There's some things that are incorrect. Like maybe I'm showing it something from a movie or a cartoon that's just not correct. And so it's got to learn like what is correct out of this and what it should actually pay attention to when it's then training this model. And then when it's outputting that model, again, it's just then predicting however you're trying to do a prediction on it. It's trying to then it's inferencing that giant neural network and saying what's the most logical output mathematically of this. And you can inference on these as saying, give me a 3D model, give me a video, give me reasoning text. So you could say like a reasoning text could be like, here's the scene, describe what in the scene would happen next, or what in the scene is incorrect, like if it's trying to find things that are false, things like that. So depending on what it does, just does different math and predicts a different output.
Mhm.
Much as the black box is ChatGPT is.
Yeah. How far are we from generative AI being able to produce full like VR movie or the VR scene that you could be able to experience in whichever VR goggles? But we could see the Genie free, but as we mentioned earlier, it was about the navigation. But how far do you think are we from the Star Trek? Was it in Star Trek where they had this room where it just simulated another world and then you were moving around and doing stuff?
I think part of it is there's one problem with this technology that I think that we're solving that just really needs to be solved, and then we could start doing this is I mean, what you're kind of talking about is like Tesla's autopilot simulator, right? You're driving around in this world. There's no reason why you couldn't have done that in a VR headset. But there's a problem that as you go along, it's called long tail predictions, where they will, or long horizon, where you can play out a scene for a minute. And then maybe after a minute, there's small little errors just making little wrong predictions of what's happening next. Well, those compound. And over 5 minutes, things start to really fall apart. Now they have ways to get around that. They're getting better and better at that. But that's like the big thing that we need to solve is how do I do these really long predictions without things starting to go wrong, or else things really go wrong quick after a while, because they come.
But it's very similar to language models, right? From the very first versions of ChatGPT, it was also like you could ask like 4 or 5 following questions, but after that it just got mixed.
It forgot all context after like 5 prompts. Now you can prompt for like, you know, these really long prompts, and occasionally I'll forget things, but yeah, so that's part of it. It's just you got to make sure it's remembering. Now they're doing things called like autoregressive. So it'll like predict out a certain 30 seconds, and then it'll seed the next 30-second chunk based off of the end of the last one. And so it's not. There's things that you can do to get around it. I know they can go now minutes, but if we're talking like a full-length movie, maybe it's an hour, 2 hours. We're not there yet.
So. Where do you see the future?
I'm hoping that we all have. I hope robots do play a big role in our future. I think we'll be safer and better off for it. It's not going to destroy all our jobs. There's going to be a whole nother class. There's going to be people who are going to lose jobs in that transition, but I think about like my aging parents. I'm not able to be there to help all the time. Them to have a robot at the home helping them or do some basic tasks would be great. Driving them around.
What do you think? What do you think about Elon's high universal income theory?
Yeah, I don't know about
prediction, more prediction than theory.
Yeah, I have no idea if universal basic income. I don't know if that'll ever come true. I think politically that'd be impossible, but you know, I just hope in the future, yeah, all this AI is helping us for good and not just creating entertainment. Entertainment's great, but I think that it's harder to get an AI to interact with the physical world than people realize. So it's going to take a long time. But as it starts to materialize, I think that we're all going to be better off. I mean, some of the first jobs that they're doing these humanoids in factories for are to move really heavy objects to and fro. I can tell you, working in industrial environments, the people who are doing that are usually getting workers' comp because over time their bodies just degrade. And so we're replacing those jobs that no one really wants in the first place. And hopefully we're able then to quickly train new people to work on robots, work on AI systems, work on all this, and be technicians. Like think of all the mechanics in the world, and that might like triple as we have all these, like robot mechanics out there working on different. You might be certified to work on a certain set of robots. That could be the future.
Where do you see the main bottleneck right now? Is it the technology in terms of amount and power of GPUs, or is it the energy source, or where do you see right now the bottleneck of like next giant leap in AI and connected to all the visual technologies that we're experiencing?
That's a good question. I think the bottleneck might be, it's a mix. Like right now, it's just getting good data to train these. Like we've exhausted the data. All the easy, low-level data is to train all these AI systems have been consumed. Getting higher quality data is tough. So that's just going to take effort and purpose. There is a lot of just research, figuring out like what's the best mix of data to train AI and improving those algorithms. I think that's a lot coming along with that. And then I think these world models are going to be like that synthetic data layer, because we can only create data at 1-to-1. If I had to create data of like picking up this cup and taking a sip out of it, I could have someone sit there for 8 hours collecting data doing that. That's 8 hours for 8 hours of data. Imagine if I could have someone do this for an hour, and a world model can now predict 1,000 hours of someone drinking a cup in different variations to train these models.
It was the similar development in web. We went from web 1.0 to web 2.0, and the difference was that we went from several people creating the content into general public creating the content, right? So something similar should happen here. Like, okay, right now, all the companies developing AI are using sources that they already have, but they need like amount of the data on totally different level. So this is just a stupid idea, but all the people wear 360 cameras on your heads or wherever, on your clothes, on your cars, wherever. And this could be an amount of data that they actually need for the next step, right? With the development.
It's just almost an infinite data collection game, because the world is infinitely complex and messy. So unlock's going to come, but it's going to be incremental. It's not going to be like this one day everything's just magically overnight going to get a lot better, which I think is good. I think for self-driving cars, where you have all these ADAS, these automatic detection and avoidance systems in your cars that are already taking over for braking and keeping you in lanes, we're just going to get to that point where like self-driving is not going to be a big deal, because we're already halfway driving, halfway not. So, I think that's what
it can be about the incentives for people, because, for example, for cars to be collecting data, there should just be a nice model for drivers, which give them some feature or some benefits if they install 360 camera on the top of their car, right?
Yeah.
And they can be collecting like endless amount of the data for corporations. I know that people will start thinking about the security and everything else about the privacy and data, but just imagine here, this could be a source of endless data if all the drivers were just driving with 360 cameras.
Yep. Well, I would love to stay on this conversation longer, but I actually had to go pick up my daughter from to take her.
No, I think right now we are just hallucinating like ChatGPT. So I think we went through all the important things that we wanted. I'm happy that you nudged me into this with your DM 2 weeks ago. It was a great talk. Thank you very much for being a part of it.
Oh yeah, people have questions. Ask, you can always hit me on LinkedIn, or I'm on X. I'm everywhere. So jump on my YouTube videos and grind me on the what I presented, because again, I can be wrong on things, but that's how we all learn.
Yeah, perfect. I have just last asked for you, Jonathan. There will be questions on LinkedIn, so please come back.
I will
in a few hours or maybe tomorrow, and just try to answer them. Guys, I have a last plug here, commercial. We are doing this 3 days conference in Prague in May. Make sure to come. We are going to focus on 3D Gaussian splatting. There will be great partners. XGRIDS will be there. Several other either processing companies or hardware software producers. There will be. We'll have amazing speakers again. So just make sure to come to Prague, and you will find all the information on 3days.com. Thank you very much for watching, and see you next week. Bye.